we're going to take a look here at combining random variables. So a few of the rules that we have for combining random variables, if we add or subtract a constant, this is just like we did before. You'll add or subtract that constant by the mean. Standard deviation, if we add or subtract a constant, it won't change the standard deviation. And if we multiply by a constant, or whether it's the mean or the standard deviation, you're going to multiply both of those things um, in the end. If we multiply by a, the standard deviation is multiplied by a. If we multiply by a, the mean is multiplied by a. So this isn't anything new. This is actually back from Unit 1 when we did this. And if we look at one of the examples that we just did in the last couple of days with this insurance policy, if you recall, those were the probabilities associated with each of those probability. So the expected value on any given insurance policy was $89, and the standard deviation, $260.54. We found those values by putting this particular table into list 1 and list 2, right? And then we told the calculator L2 is a frequency list. So a way that's going to be a little bit different for us is all of a sudden if we decide that we're going to find the expected value and standard deviation, if we decide to start charging customers instead of $100 a year, 10 times the amount, which would be $1,000 a year. So the expected value now for 10x, this is where we were using that rule before. It just means we're going to multiply the $89. So instead of $89, we're now expecting to make $890 for every policy. And then the standard deviation, if we multiply by 10, the rule says if you multiply by a constant, we multiply both by a constant. And so you'll have to excuse the messy writing here, but that'd be $2,605 and then 40 cents. All right. And another approach to this, let's say the company decided, well, instead of charging everybody 10 times more, we're actually going to charge everybody $15 less. So here's the example where we're adding or subtracting a constant. So here it's x minus 15. And the rule states that if we subtract 15 from the mean, then or from each of the values, then we'd subtract 15 from the mean. So now the expected profit per policy is $74. And because everything's being subtracted by 15, the original standard deviation is not going to change. So we're still at that $260.54. When things start to change for us, however, is if we look at this example, this guy weighed a lot of pennies, and not every penny was the same, but the average weight was 3.11 grams, and there's a standard deviation of 0.43. So then, if we wanted to combine, what are the reasonably likely mean and standard deviation for a roll of 50 pennies? So if x is our single penny, I should say, so this is actually a single penny, um, then these will be normally distributed. That's what that big N is for. And, right, just as a quick reminder, and then there's the mean, 3.11. There's the standard deviation, 0.43. If we did 50 pennies, what makes this a little bit different is we're not actually doing any kind of conversion, so we're not multiplying by 50. We're not readjusting the scale, so it's not like, oh, we need to subtract, 0.5 grams, our scale was off. This is actually a different look because we're combining penny after penny after penny after penny. And so when we start to combine random variables, there's a couple new rules for us. First off, the mean, when we combine them, all you're really going to do is the mean of x, right? Keep in mind, expected value is just mean, and then the mean of y. So mean of x plus the mean of y. To do standard deviation, the one thing we need to realize is we always need to add variance. So to get it back to standard deviation, so the standard deviation of x plus or minus y is going to be standard deviation of x squared, that's the variance, x, plus the standard deviation of y squared. But what we want to make sure that we do is we come back and we take the square root of all of that, because we converted both the original standard deviations into variance. But the big thing to remember, variances always add. So quick example here. Let's say that we have these independent random variables x and y. So maybe we'll say x is the number of years a dog lives, and then y is number of years a cat lives. So dogs on average live about 10 years with a standard deviation of 2 years. Cats live on average 20 years, standard deviation of 5. I don't know if that's really true, but we'll use it for this take the example, and we'll go through those uh, 5 different ways. So the first thing with A is literally just we're going to multiply through by a constant. So there's the table again. So 3x be 3 times 10, and then standard deviation 3 times 2. Right? So this is just 3 times 2. And that's just using that rule back from like Unit 1. Let's say that we were off with our cats. We said, oh, cats actually live 6 years longer than we thought. So we'll come back to our mean of 20, and we'll add the 6. But because we added 6 to every cat's life, the standard deviation doesn't change. Again, this is Unit 1 when we did some of the linear transformations. However, let's say that someone has a cat and a dog, right? And they want to see how long is it they're going to have a dog first, and then they're going to go buy a cat. So how long will they have a pet companion? Well, that would be x plus y. So the expected value is pretty easy. You literally just add the means. The standard deviation is a tricky one, and this is where I recommend come over here after standard deviation and create an extra section for variance. And all the variance is just standard deviation squared. And so what you're going to do with this, in order to get the standard deviation of x plus y, what you're actually going to have to do is add the variances, because variances always add, and then take the square root of that, which is how we get this 5.385. If we did x minus y, again, maybe this is how much longer do we expect our dog to live? Well, dogs live shorter, so we'd expect a negative 10 years. And standard deviation of x minus y, this is a big thing to realize, because a lot of people are going to do this wrong if they're not careful. What you end up having to do, again, variances always add. So again, we want to do the square root of the variances, right? And I mentioned, hey, let's make sure that we're changing standard deviations into variance. And doing this step 2 will also help kind of jog your memory. Okay, I need to make sure that I deal with this column, not the standard deviation column. I don't want to deal with this column when I start to add stuff. So that's 4 plus 25, which is again the 5.385. And although it seems kind of counterintuitive, why are we adding things when our random variables are being subtracted? Well, if you want to think about it this way, we're putting two distributions together. And anytime you start putting more things together, you get more variance. You get more variation in general. So even though we're subtracting, that just happens to be how we're combining them. We're still combining two different things, which means we're going to have more variability, which means you need to add. And then that part E, so let's say that we're going to buy or get 2 dogs in a row. So again, expected value, very straightforward. 10 plus 10 is 20. To get this standard deviation, again, we're not being asked 2x. This is not the same thing, so it's not equal to 2 times x. If they wanted the expected value of 2x, they would have asked for 2x. Kind of like in A, they asked for 3x. These are not the same thing. So we're just going to have to add 10 plus 10. The standard deviation of x1 plus x2, again, we need the variance of x1, which is 4, and then the variance of x2, which is 4 again, and we're going to take the square root of that, and that's where that 2.828 comes together. So a real-world example really quickly before we close this video out. So suppose the average SAT math score is 625 with a standard deviation of 90, and the average SAT verbal is 590 with standard deviation of 100. So let's find the mean and standard deviation of composite scores. So let's say X is going to be defined as math scores. They're normally distributed. Remember, this is mean, and this is standard deviation. And then Y, verbal scores, normally distributed around 590 to 100. So typically students do better on math, but there's more variation, so scores are a bit more spread out over here on verbal. So when we're looking for what is the mean and standard deviation of the composite scores, we're looking for x plus y. So what does that distribution look like? Well, if we go back through, I'll just rewrite all that. So we have it, the expected value of x plus or minus y is expected value of x plus or minus the expected value of y, or in our case, we take the mean of x plus the mean of y, 1215. In order to get the variance, we need to square 90. That's where that 8100. You need to square 100. That's where that 10,000. Then to get that standard deviation, we'll just take that square root and we end up with a score of, or a standard deviation of 134.5 points. And again, if you think about it, you kind of do a rough estimate. About 68% of people are going to score somewhere probably between just below 1100 at about 1350, which makes perfect sense for us.